All right. Oh, okay. All right, good morning. I'm about to start my bit where I just sit here and talk for a couple seconds to make sure that everything's going good. And I'm a little confused because I see that the button says go live and not streaming, but I can hear my voice and see my stream, so I think we're good. Good morning. It is, well, for me, if it's not morning for you, good day, I guess. I know we're getting started a little bit early, but I figured I would get my sitting here talking to myself while I wait for the stream to catch up off started with early. So today we are jumping back into the Kaggle reading group, and we're going to be reading something that's been sitting on my desk, metaphorically staring at me for a bit, and that is reading the new chapters from the third edition of Speech and Language Processing, which is available online. And if you're not familiar, good morning, Ilya. It's 6 p.m. in Eastern Europe. Well, good evening then. Speech and language processing is the hello, Fabiana. That's I'm guessing with. Thanks for tuning in from Brazil. Speech and language processing. It is the I don't want to say the default, but probably the most popular textbook for teaching natural language processing. I actually have a physical copy of it here on my desk. I'm just gonna flip it near the microphone. That's great audio. Hello, Sheik from India. Welcome. And the version that I have a physical copy of is actually, it's the first edition, so it's a little bit out of date. And there have been a lot of updates, and there have been some new chapters. And you can see I've been looking at some of them. And I wanted to go through and read all the new chapters just to sort of like see what's up. Because I read a lot of papers, but it's good to know the basics that it's expected that you're going to know if you're working in the field, especially like dependency parsing, all of this parsing stuff. I am going to read it. I read it in the first edition, but I think it's changed quite a bit. And I will go back and do this naive Bayes classification at some point, but it's a lot of math, and I don't know that I'm up to that much math first thing in the morning. So instead, we're going to start with chapter 7, which is new in this third edition. And the link is in the video description if you want to read along. Neural networks and neural language models. And I'm just going to start reading and take little detours as we get to things that I think need more explanation or I have questions about. So it starts off with a quote, and this is a draft, by the way. So if there's typos or anything, it's we can leave some comments and let Daniel and Jean know. All right, so it starts with a nice little quote. Machines of this character can behave in a very complicated manner when the number of units is large, from Alan Turing, Intelligent Machines, 1948. And just an aside, when I was learning language modeling, which is what this chapter is about, neural networks were not the thing that I was taught. I was taught n-grams. So nothing wrong with a good n-gram language model, but it's a little bit old school at this point, apparently. Zoom in. So, neural networks are an essential computational tool for language processing and a very old one. They are called neural because their origins lie in the McCulloch-Pitts neuron, McCulloch-Pitts 1943, a simplified model of the human neuron as a kind of computing element that could be described in terms of propositional logic. But the modern use in language processing no longer draws on these early biological inspirations. Instead, a modern neural network is a network of small computing units, each of which takes a vector of input values and produces a single output value. So it maps many things onto one thing. In this chapter, we introduce the neural net applied to classification. The architecture we introduce is called a feedforward network because the computation proceeds iteratively from one layer of units to the next. So it's not recurrent. It doesn't like form a loop. The use of modern neural nets is often called deep learning because modern networks are often deep, have many layers. Oh, and there's a nice little sidebar here, so you can find the term definitions easily. That's nice. Neural networks share much of the same mathematics as logistic regression, but neural networks are a more powerful classifier than logistic regression, and indeed a minimal neural network, technically one with a single hidden layer, can be shown to learn any function. Neural net classifiers are different from logistic regression in another way, and I'm pretty sure logistic regression is covered in an earlier chapter if you want to go back and read that. With logistic regression, we applied the regression classifier to many different tasks by developing many rich kinds of feature templates based on domain knowledge. When working with neural networks, it is more common to avoid the use of hand-derived features, instead building neural networks that can take raw words as inputs and learn to induce features as part of the process of learning to classify. We saw an example of this kind of representation learning for embeddings in Chapter 6, which we haven't read. Hi, Janth. A super interesting topic. I agree. Nets that are very deep are particularly good at representation learning for that reason. Nets that are very deep are particularly good at representation learning. For that reason, deep neural nets are the right tools for large-scale problems that offer sufficient data to learn features automatically. So this is sort of placing neural networks in as a different approach than building rules and rule-based systems, which for years and years and years were state of the art. In this chapter, we'll see feedforward networks as classifiers and apply them to the simple task of language modeling, assigning probabilities to word sequences and predicting upcoming words. In later chapters, we'll introduce many other aspects of neural networks, of neural models, such as the recurrent neural network and the encoder-decoder model. Okay. Yeah, hopefully we'll talk a little bit more about language modeling and why it's interesting. I don't want to talk about it too much in case there's a whole big section of it that we can read. 7.1, units. The building block of a neural network is a single computational unit. A unit takes a set of real-valued numbers as input, performs some computation on them, and produces an output. So, kind of like a function? A little bit. At its heart, a neural unit is taking a weighted sum of its inputs with one additional term in the sum called a bias term. Thus, given a set of inputs x sub 1 to x sub n, a unit has a set of corresponding weights w sub 1 to w sub n and a bias b, so the weighted sum z can be represented as, I've got to read equations, z equals b plus the sum to the ith term of w sub I x sub I. So you take all of your inputs, you multiply each of them by the weights, you add the product of each weight and each input, and then you add the bias term. Often, it's more convenient to express this weighted sum using vector notation. Recall from linear algebra that a vector is, at heart, just a list or array of numbers. Thus, we'll talk about z in terms of a weight vector w, a scalar bias b, and an input vector x, and we'll replace the sum with the convenient dot product. So z is the dot product of w and x plus b. Sorry, that was equation 7.2. The sigma one was equation 7.1. As defined in equation 7.2, z is just a real valued number. Finally, instead of using z, Koshik says, thanks a lot, Rachel. You're welcome. Finally, instead of using z, a linear function of x, as the output, neural units apply a nonlinear function f to z. We will refer to the output of this function as the activation value for the unit a. Since we are just modeling a single unit, the activation for the node is in fact a final output of the network, which we'll generally call y. So the value y is defined as y equals a equals f of x. Activation. Okay, so when we apply the function, the nonlinear function f to z, that's the activation, and then the activation is also the output. Okay. We'll discuss three popular nonlinear functions f below: the sigmoid, the tan, and the rectified linear unit. Rectified linear ReLU. I would probably here say the rectified linear and then put ReLU in parentheses, but they're the same thing. but it's pedagogically convenient to start with the sigmoid function since we saw it in chapter 5, which we haven't read. Okay. Y equals, so that's sigma of z equals 1 over 1 plus e to the negative zth power. The sigmoid, shown in figure 7.1, has a number of advantages. It maps the output onto the range 0, 1, which is useful in squashing outliers towards 0 and 1, and it's differentiable, which we saw in section question mark, will be which, as we saw in section question mark, will be handy for learning. Again, this is a draft. So if we look at figure 7.1, we can see a representation of the sigmoid, which looks sort of like an esh. It sort of looks like a squashed S, where you take each of the lines and pull them to the side that they're pointing towards. The sigmoid function takes a real value and maps it to the range 0 to 1. Because it is nearly linear around 0, but has sharp slopes towards the end, it tends to squash outlier values towards 0 or 1. So if I'm in this range nearish 0, I'm going to be closer to 0.5. If I'm in this range very far from 0 and positive, I'm going to be closer to 1. And if I'm in this range very far from 0 and negative, I'm going to be closer to 0. Let's go back up. Substituting the sigmoid equation in equation 7.2 gives us the final output for the final value for the output of a neural unit. Siddharth says, "Hey Rachel, thanks for the live feed." You're welcome. And sorry for trying to read math out. This is great. All right. Y equals, so this is the final output of a neuron. A unit, sorry. We haven't said the word neuron. Sigma. That's like a lowercase sigma, right? I'm like 90% sure that's a lowercase sigma. Yes, lowercase sigma, and then it gives it in Greek. That's very helpful. Lowercase sigma of the dot product of w and x plus b equals 1 over 1 plus exp, the exponent, I guess. What does exp mean? Explore our architecture and design capabilities. exp. That's not helpful. Exponential function. Yeah, the exponential function, negative, the dot product, and the next thing I'm going to say, the whole thing is negative, the dot product of w and x plus b. And that is equation 7.5. Figure 7.2 shows a final schematic of a basic neural unit. In this example, the unit takes 3 input values, x1, x2, and x3, and computes a weighted sum, multiplying each value by a weight, w1, w2, and w3 respectively, adds them to a bias term b, and then passes the resulting sum through a sigmoid function to result in a number between 0 and 1. Sheik says exponential. Thank you. There's a little bit of a delay. And so we have here our figure. So a neural unit taking 3 inputs, x1, x2, x3, and a bias b that we represent as a weight for an input clamped at +1. So it can't be more than 1. And producing an output y. We include some convenient intermediate variables, the output of the summation z and the output of the sigmoid a. In this case, the output of the unit y is the same as a, but in deeper networks we'll reserve y to mean the final output of the entire network, leaving a as the activation of an individual node. Oh, okay, so that's why we've broken them apart. Because if you will remember from equation 7.3, there was just this one that was like y equals a equals f of z, where f is the activation function. And so far we have learned about the sigmoid activation function, which looks like an S. Let's walk through an example just to get an intuition. Let's suppose we have a unit with the following weight, vector, and bias. Scroll down. So the weight vector is 0.2, 0.3, 0.9, and the bias is 0.5. What would this unit do with the following input vector? X, the input x is 0.5, 0.6, 0.1. So we would multiply 0.5 by 0.2, 0.6 by plus 0.3, 0.1 times 0 plus 0.9, add them all together, then add the bias function, and then apply our sigmoid activation. And that's what we see here. So this this is the multiplication and addition I just talked about. And then we apply the sigmoid activation function, which is here as sigma, and here is just all of that's been broken down into its component parts. So it's e to the negative 0.87th power, and the output is 0.70. I don't expect anybody to be able to do that math in their head. That's a lot. In practice, the sigmoid is not commonly used as an activation function. True. A function that is very similar, but almost always better, is the tan function shown in figure 7.3a. Tan is a variant of the sigmoid that ranges from -1 to +1. So here, we see the sigmoid is bounded at 1 and 0. Instead, tan goes to 1 to -1. So if we're very close to 0, our output is going to be around 0. And as we get more positive, our output's going to be closer to 1. And as we get more negative, our output's going to be closer to -1. Where was I? Y equals e to the zth minus e to the negative zth over e to the zth plus e to the negative zth is the tan activation. The simplest activation function, and perhaps the most commonly used, is the rectified linear unit, also called the ReLU, shown in figure 7.3b. It is just the same as x when x is positive and 0 otherwise. So if we have a positive number, it's going to be the same as whatever the number was, and if the number is negative, we're just going to set it equal to 0. And I think people tend to use leaky ReLU a little bit more, which is when the input is negative. It's a very slight negative slope, so it's always pretty close to 0 unless you have an absolutely huge negative input, but that way you don't get neurons dying and having everything set to 0. But we'll get to there. That's just sort of my current impression of the field, and I could be wrong. And a little visualization here of the tan and ReLU activation functions. These activation functions have different properties that make them useful for different language applications or network architectures. For example, the rectifier function has nice properties that result from it being very close to linear. In the sigmoid or tan function, very high values of z result in values of y that are saturated, i.e. extremely close to 1, which causes problems for learning. Rectifiers don't have this problem since the output of values close to 1 also approaches 1 in a nice, gentle, linear way. By contrast, the tan function has nice properties of being smoothly differentiable and mapping outlier values towards the mean. So which you pick is going to depend on the qualities that you want. All right, section 7.2. So that is a very fast introduction to how neural networks work. We don't really talk about training at all. Perhaps we will get to there. So this is how a trained network works. And in a trained network, the weights, which are represented here by W, are provided. The XOR problem. Early in the history of neural networks, it was realized that the power of neural networks, as well as the real neurons that inspired them, comes from combining these units into larger networks. One of the most clever demonstrations of the need for multi-layer networks was the proof by Minsky and Papert, 1969, that a single neural unit cannot compute some very simple functions of its input. Consider the very simple task of computing simple logical functions of two inputs, like AND, OR, and XOR. As a reminder, here are the truth tables for these functions. Oh my god, this is like semantics all over again. So if we have two values, x1 and x2, and they are each either true or false, if we concatenate them using AND, if x1 is false and xy is false, the output will be false. If x1 is false and x1 is false, x2 is true. Danny says, hello from Indiana. Hello, Danny. Good morning. It's morning for you. Then the output will be false. So basically they both have to be true for the output to be true. In OR, either of them have to be true for, only one of them has to be true for the output to be true. And in XOR, only one of them can be true for the output to be true. More or less. Wow, that takes me back. So this is, you know, if you take two values, you should always get a deterministic output if you have the same, you know, logical function that you're using. Danny says, it's noon, Rachel, 12 p.m. Ah, beans, I'm bad at time zones, I'm sorry. Well, good afternoon. So we should be able to deterministically figure out if x1 is 0 and x2 is 0, that y is always going to be 0 if we're using AND or XOR. This example was first shown for the Perceptron, which is a very simple neural unit that has a binary output and no nonlinear activation function. So the activation function like tan or sigmoid is not going to be used here. Jan says, that's a great explanation of AND or XOR. I still struggle with them. Whoop, knocked my book off my desk. I still struggle with them a bit. Yeah, the thing that's hardest is that OR in natural language, at least in English, if both are positive, then it doesn't make sense to say that it's true that one or the other is positive. Like it makes sense, it's logical, but that's the thing that I got wrong on tests a lot. Semantics was not my favorite. But it was very useful, and I have used the formal logic. I learned a lot, so thank you, Toshi, for teaching me semantics, even though I was not especially grateful at the time. All right, where were we? So they don't have a nonlinear activation function. The output y of a perceptron is 0 or 1, and just computed as follows. Using the same weight w, input x and bias b as in equation 7.2. So y is 0 if the dot product of w and x plus b is greater than 0, less than or equal to 0, and it is 1 if the dot product of w and x plus b is greater than 0. So it's instead of like a smooth thing here, we just have actually the sigmoid's a better example. Instead of this smooth thing here, we just have like a little step function where if it is 0 or less than, it's equal to 0, and if it's greater than 0, it's equal to 1. Where were we? The XOR problem, here we go. It is very easy to build a perceptron that can compute the logical and or functions of its binary inputs. Figure 7.4 shows the necessary weights. So the weight for, I'm going to read this and then I'm going to talk about what I think it means. The weights W and bias B for perceptrons for computing logical functions. The inputs are shown as x1 and x2, and the bias is a special node with a value +1, which is multiplied with the bias weight B. So this half of it, logical AND, shows weights W equals 1 and W2 equals 1, and bias weight B equals -1. B, logical OR, shows weights W1 and W1 is 1, W2 is 1, and bias weight B equals 0. These weights/biases are just one from an infinite number of possible sets of weights and biases that would implement the functions. So if we look back up at this table, I'm going to zoom out a little bit so we can see both of these at the same time. There we go. So if we look back up at this table, this one shows us and if x1 is 0, times 0 is 1, so this is going to be 0, and x2 is 0 times 1, so it's also going to be 0, and then our bias function is going to be -1, so we've got 0 plus 0 minus 1, and given our activation function, that's going to set our weight to 0, then y, our output, is going to be 0 using this network. On the other hand, if x is 0 and x1 is 0 and x2 is 1, then x1, 0 times 1 is going to be 0, 1 times 1 is going to be 1, -1, so 0 plus 1 minus 1 is 0, so the output is going to be 0. And then 1 times 1 is 1, 1 times 1 is 1, minus 1 is 1, because it's 2 minus 1, and given our activation function, that's going to be 1, so the output's going to be 1. And then we can step through the same thing for OR. But basically, both of these networks are going to give us the same input and output as these truth tables. And I'm going to zoom back in so we can actually read stuff. It turns out, however, that it's not possible to build a perceptron to compute logical XOR. It's worth spending a moment to give it a try. Is it? I've only had one coffee today. I'll leave that as an exercise to the watcher. The intuition behind this important result relies on understanding that a perceptron is a linear classifier. For two-dimensional input, x0 and x1, the perceptron equation, w1x1 plus w2x2 plus b equals 0, is the equation of a line. We can see this by putting it in the standard linear format. x2 equals negative w1 divided by w2 x1 minus b. So this is like mx plus b, or in this case minus b. This line acts as a decision boundary in two-dimensional space in which the input 0 is assigned to all inputs lying on one side of the line, and the input 1 to all inputs lying on the other side of the line. If we add more than two inputs, the decision boundary becomes a hyperplane instead of a line, but the idea is the same, separating the space into two categories. So basically, if you have a chart of all your points, a decision boundary that we are describing in this way can only be straight. You can't draw like a circle. Figure 7.5 shows the possible logical inputs 0, 0, 0, 1, 1, 0, and 1, 1, and the line drawn by one possible set of parameters for an and an or classifier. All right, where's 7.5? Here we go. So you can see this is straight. The functions AND, OR, and XOR, represented with the input x0 on the x-axis and the input x1 on the y-axis. Why can't we just call them x and y? I'm making hand gestures. We're going to call them x1 and x2. Filled circles represent perceptron outputs of 1, and white circles perceptron outputs of 0. There is no way to draw a line that correctly separates the two categories for XOR. Figure styled after Russell and Norvig, 2002. So here is the AND perceptron, and here are the inputs, and the color represents the output of the perceptron. And so there's a way to draw one line that separates the AND space, one line that separates the OR space. You cannot draw one straight line that separates the XOR space. Scroll up. Where were we? Blah, 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 blah. Notice that there is simply no way to draw a line that separates the positive cases of XOR, 0, 1, and 1, 0, from the negative cases, 0, 0, and 1, 1. We say that XOR is not a linearly separable function. Of course, we could draw a boundary with a curve or some other function, but not a single line. 7.2.1. The solution, neural networks. While the XOR function cannot be calculated by a single perceptron, it can be calculated by a layered network of units. Let's see an example of how to do this from Goodfellow et al. 2016 that computes XOR using two layers of ReLU-based units. Figure 7.6 shows a figure with the input being processed by two layers of neural units. The middle layer, called H, has 2 units, and the output layer, called Y, has 1 unit. A set of weights and biases are shown for each ReLU that correctly computes the XOR function. All right, let's look at 7.6. Here we go. XOR solution after Goodfellow et al. 2016. There are 3 ReLU units in 2 layers. We'll call them H1, H2, and Y1. As before, the numbers on the arrows represents the weight W for each unit, and we represent the bias B as the weight on a unit clamped to +1, with the bias unit's weights in gray. So I think by clamped they mean bounded by +1 and -1. This is not a term I have heard before. You know what? I will look that up later. That seems like something that might get unfortunate results. Okay, so here is our neural network. Here is X1, here is X2. These are the weights. So the weights going to the first hidden layer from x1 are both 1. The weights going to the first hidden layer from x2 are both 1. The bias for h1 is 0. The bias for h2 is -1. And then the weights of these outputs going from h1 to y1 is 1, from h2 to y1 is -2, and then the bias term for this final unit is +1. So let's work through the situation where both x1 and x2 are 0. So 0 times 1 is 0, 0 times 1 is 0 plus 0, so the output of this is going to be 0. 0 times 1 is 0, 0 times 1 is 0, minus 1, so this is going to be -1. So here we have 0, here we have -1. 0 times 1 is 0, -1 times -2 is 2, plus 1. Oh, wait. That's right. We had a simple linear activation. I forgot to apply my activation. Does it say what the activation for this is? Units clamped to 1, where the bias weights are 7.6. 2 middle layer, 2 units. Oh, they're gonna walk us through. Okay. Let's see what the activation was, because I definitely missed that. Let's walk through what happens when the input x equals 0, 0. If we multiply each input value by the appropriate weight sum and then add the bias b, we get the vector 0, -1, 0, -1. And then we apply the rectified linear transformation given the output of the h layer as 0, 0. Okay, so that's right, because if it's positive, it goes to 1. If it's greater than 0, it goes to 1. If it is 0 or less, it goes to 0. So these are both going to be 0. Now we once again multiply by the weights sum and add the bias, 0 in this case. So 0 times 1 is 0, 0 times -2 is 0, plus 1 is 1. The reader should work through the computation of the remaining 3 possible input pairs to see the resulting y values correctly are 1 for the input 0, 1 and 1, 0, and 0 for 0, 0 and 1, 1. Relu Eunice, Sheik says, oh, is there a U-N-I-Y-S? I thought you might be pointing out a typo, but I don't see it. No, I lost my place. Scroll. There we go. So let's work through 1, 1. So 1 times 1, 1 times 1, plus 0, so this is going to be 1. 1 times 1, 1 times 1, so it's 2, minus 1 is 1, so this is going to be 1. 0 and 1. 0 times 1 is 0. 1 times -2 is -2. So we're at -2 plus 0. So that's going to be 0 because negatives go to 0. So if the outputs are both 1, the inputs are both 1, the output is 0. Oh, the activation was Relu. Thank you, Sheik. So yes, if the inputs are both 1, then the output is 0. It is also instructive to look at the intermediate results, the outputs of the 2 hidden nodes, h0 and h1. We showed in the previous paragraph that the h vector for the inputs 0, 0 was 0, 0. Figure 7.7b shows the values of the h layer for all 4 inputs. Notice that hidden representations of the 2 input points, x01 and x10, the 2 cases where XOR input equals 1, are merged into a single point, h equals 1, 0. The merger makes it easy to linearly separate the positive and negative cases of XOR. In other words, we can view the hidden layer of the network as forming a representation for the input. There we go. So if we're looking in this x1, x0 space, we can't draw a simple line to separate them, but by using the hidden layers instead as our representation of our decision space, we can easily draw a single line to separate them. The hidden layer forming a new representation of the input. Here's the representation of the hidden layer, h, compared to the original input representation, x. Notice that the input point 0, 1 has been collapsed with the input point 1, 0, making it possible to linearly separate the positive and negative cases of XOR, after Goodfellow et al., 2016. All right. In this example, we just stipulated the weights in figures 7.6. But for real examples, the weights for neural networks are learned automatically using the error backpropagation algorithm to be introduced in section 7.4. Oh, good, we are going to talk about training. This means that the hidden layers will learn to form useful representations. This intuition that neural networks can automatically learn useful representations of the input is one of their key advantages, and one that we will return to again and again in later chapters. Note that the solution to the XOR problem requires a network of units with nonlinear activation functions. A network made up of simple linear perceptron units cannot solve the XOR problem. This is because a network formed by many layers of purely linear units can always be reduced, shown to be computationally identical to, a single layer of linear units with appropriate weights. And we've already shown visually in figure 7.1 that a single unit cannot solve the XOR problems. So critically, we need to have a nonlinear activation function. So something like the ReLU or the TAN or the sigmoid that we talked about earlier. Whew, okay, 7.3. Feedforward neural networks. We are not getting through this chapter today. We're going to have to make this one a two-parter. That's okay, this is pretty dense. Let's now walk through a slightly more formal presentation of the simplest kind of neural network, the feedforward network. A feedforward network is a multi-layer network in which the units are connected with no cycles. The outputs from units in each layer are passed to units in the next higher layer, and no outputs are passed back to lower layers. So if we were talking about this in terms of graph theory, this would be a directed acyclic graph. We can't draw a cycle through the graph where we can get back to a unit that we were looking at before, or a node that we were at before. That may or may not have been helpful for y'all. In chapter 9, we'll introduce networks with cycles called recurrent neural networks. Ugh, fancy. For historical reasons, multi-layer networks, especially feedforward networks, are sometimes called multi-layer perceptrons, or MLPs. This is a technical misnomer, since the units in modern multi-layer networks aren't perceptrons. Perceptrons are purely linear, but modern networks are made up of units with nonlinearities, like sigmoids. But at some point, the name stuck. Yeah, I've definitely heard that. Simple feedforward networks have three kinds of nodes. She says, DAGs like in Spark. Yes. Have three kinds of nodes: input units, hidden units, and output units. Figure 7.8 shows a picture. And this is something that if you've been working in neural networks at all, you've probably seen something like this. So here we have our inputs. Here we have our bias, which is the same for each of these. We have our hidden layers and then our output layers. A simple two-layer feed-forward network with one hidden layer, one output layer, and one input layer. The input layer is not usually counted when enumerating layers. The input units are simply scalar values, just as we saw in figure 7.2. The core of the neural network is the hidden layer, formed of hidden units, each of which is a neural unit as described in section 7.1, taking the weighted sum of its inputs and then applying a nonlinearity. In the standard architecture, each layer is fully connected, meaning that each unit in each layer takes as an input the outputs from all the units in the previous layer, and there is a link between every pair of units from two adjacent layers. Thus, each hidden unit sums over all the input units. So that just means that x1 feeds into all of the other units, x2 feeds into all of the units in the layer above it, and so on. So there's not like a missing link between x sub n sub 0 to the second hidden layer. We've read that. Recall that a single hidden unit has parameters w, the weight vector, and b, the bias scalar. We represent the parameters for the entire hidden layer by combining the weight vector W sub I, and bias B sub I for each unit I in a single weight matrix W and a single bias vector B for the whole layer. Represent the parameters. Sorry, like halfway through that sentence, my brain just turned off. By combining the weight vector W sub I and the bias B sub I for each unit I in a single weight matrix W. So this is the weight matrix. Weight vector. I see. I see. So each unit has its own vector of weights, and the matrix is a matrix where each column, or each row, I guess, are the weights for a single unit at that layer of the network. All right, I'm following now. My brain turned back on. And then there's a single bias vector B for the whole layer. So this weight matrix W is the input into, or sorry, the output of each of the, they're not perceptrons because it's probably not linear, each of the units, and then the bias vector is just going to be the same across the whole weight matrix rather than having a different bias for each unit like we saw in this example. So this has a different bias for each unit, and in this example we have the same unit, the same bias for each unit in the same layer. So that's a key difference from the example that we were looking at earlier. Okay, each element W sub I sub j of the weight matrix W represents the weight of the connection from the ith input unit x sub 1 to the jth hidden unit h sub j. Each element of W sub I sub j, so in this matrix we're looking at the ith, let's just pick one as a row, one as a column. So the input unit, we're going to say, are in rows, and the weights are in columns. So the element is going to be the product of the input and the weight. The advantage of using a single matrix W for the weights of the entire layer is that now the hidden layer computation for a the advantage of using a single matrix W for the weights of the entire layer is that now that hidden layer computation for a feed-forward network can be done very efficiently with simple matrix operations. In fact, the computation only has 3 steps: multiplying the weight matrix by the input vector x, adding the bias vector b, and applying the activation function g, such as sigmoid, tan, or ReLU activation function defined again. This used to be f. Why did we change what it was? The input of the hidden layer, the vector h, is thus the following, using the sigmoid function sigma. So h is sigma, the weight matrix times x plus b, where x is the input vector. Okay. So, when I said earlier that the weight matrix was the product of the input and the weight, I was wrong, and that was not what it is, actually. Okay. Notice that we're applying the sigma function here to a vector, while in equation 7.4 it was applied to a scalar. We're thus allowing sigma dot, and indeed any activation function g dot, to apply to a vector element-wise. So g, z1, z2, z3 is g of z1, g of z2, g of z3. Let's introduce some constants to represent the dimensionalities of these vectors and matrices. We'll refer to the input layer as layer 0 of the network, and use have n0 represent the number of inputs. So x is a vector of real numbers of dimension n0, or more formally, x is the sum of all real numbers sub 0? That can't be right. So a vector of real numbers is a set of real numbers with a dimension and 0. Okay. Let's call the hidden layer layer 1 and the output layer layer 2. The hidden layer has dimensionality n sub 1. So h is, what does this mean? I'm just gonna Google it. Element in the set. So more formally, x is an element in the set of real numbers of the dimension n0. So h is an element of the set of real numbers of dimension n1, and b is also an element in the set of real numbers of dimension n1. Jan says belongs to. Thank you. Each hidden unit can take a different bias value, and the weight matrix W has dimensionality W in the set of real numbers n of the dimension n1 times n0. Okay. I'm gonna need a second with this paragraph. Let's go back through here. Okay, so this is the number of inputs. So the input is going to be a vector that has the same dimension as the number of inputs, which is important because a neural network can handle a set number of inputs. So this could be any number that we're putting in, but they all have to have the same dimension. The hidden dimension has, what's h? Okay, h is the output of the hidden layer. So the hidden dimension has the output that is the dimension of the hidden layer. So the output of the hidden dimension, the output of the hidden layer has the same dimension as the hidden layer. So basically, each of these gets an output. And the bias is also going to be the same. So the bias is going to have the same number of dimensions as the number of cells in the hidden layer. Each hidden layer is going to have an output. And the reason we do that is that each hidden unit can take a different bias value. Vaishal says, how are you? I am bored. What are you teaching? We are reading through a chapter of speech and language processing, chapter 7, neural nets and neural language models. It's a lot of math. Is this related to machine learning or AI? Yes. Okay. And the weight matrix W has the dimensionality. So it's going to be the number of hidden layers times the number of inputs. That makes sense. Okay. I just confused myself with the set notation. Take a moment to convince yourself that the matrix multiplication in equation 7.9 will compute the value of each h sub I sub j as the sum of summing across n sub x. What was n? The R supposedly means set of real n vectors. Oh. Oop. This is very helpful. Thank you. Jan says, sorry, a bit behind. Yeah, no worries. Set of real numbers, the set of real n vectors, n times 1 matrices. Oh, that's helpful. Thank you. You can tell I don't spend a lot of time reading mathematical notation out loud. Blah, blah, blah. Take a moment to convince yourself that the matrix multiplication in equation 7.9 will compute the value of each sub I sub j as summing across each of the input numbers where you take the weights times the input plus b. I feel like I'm convinced. Vishal, you might want to start from the beginning. We've done a lot to get here. Okay. As we saw in section 7.2, the resulting value h for hidden, but also for hypothesis, forms a representation of the input. The role of the output layer is to take this new representation H and compute a final output. This output could be a real valued number, but in many cases, the goal of the network is to make some sort of classification decision, so we will focus on the case of classification. And so that's just like logistic regression. If we are doing a binary task like sentiment classification, we might have a single output node, and its value y is the probability of positive versus negative sentiment. So that's, I think I just said, that's just going to be just like logistic regression. So you have your input, and you're going to get out some probability, and you want to change that probability into a classification, but you're going to have to decide what the boundary is there. If we are doing multinomial classification, such as assigning a part of speech tag, part of speech is like noun, verb, adjective, preposition, determiner, article, we might have one output node for each potential part of speech, whose output value is the probability of that part of speech, and the values of all the output nodes must sum to 1. The output layer thus gives the probability distribution against the output nodes. So in that example, input would probably be the letters in the word, I guess. You might just have a single input that's the word, and then you have hidden layers, and then the output would be probability of being a noun, probability of being a verb, probability of being a preposition, etc., etc. Blah, 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 blah. Let's see how this happens. Like the hidden layer, the output layer has a weight matrix. Let's call it U. But the output layers may not T have a bias vector B. I think that's a typo. So we'll simplify by eliminating the bias vector in this example. The weight matrix is multiplied by its input vector H to produce the intermediate output Z. Is this what we were calling Y earlier? Jance says, also per the earlier text, probability of being a sequence of text. Yeah, I don't entirely know how we're going to get from here to language modeling. Okay. To the intermediate output Z. There are n sub 2 output nodes. Okay, so basically we're just saying that at this stage, we don't have a bias vector. So that's what the simplification is. There are n sub 2 output nodes. So Z is a vector of real numbers of dimension n sub 2. N sub 2 is the number of output nodes. So we have a vector that is the same dimension as the number of output nodes. And also, thank you again, Jance. That was super helpful. Weight matrix U has dimensionality n2, n1, where n1 was the number of hidden nodes. Where did we get n1 from? Yes, the hidden layer. So the dimension of the hidden layer times the dimension of the output layer. So it's a matrix. And element uij is the weight from unit j in the hidden layer to unit I in the output layer. Element uj is the weight. Okay, so the weight which are represented as edges in this graph. So basically we're making a matrix that represents this part of the graph. All right. However, Z can't be the output of a classifier since it's a vector of real valued numbers. Well, what we need for classification is a vector of probabilities. There is a convenient function for normalizing a vector of real values, by which we mean converting it to a vector that encodes a probability distribution. All the numbers lie between 0 and 1 and sum to 1. The Softmax function we saw on page, of chapter 5. For vector Z of dimensionality D, the softmax is defined as e to z, e to the ith z term divided by the sum of 1 to the eth to the zth j, the z term of g. Oh my gosh, sorry. This is very difficult to read. Softmax. You know what? This is not the point of this particular reading. I'll let you guys go read about Softmax on your own. Thus, for an example of a given vector, I'm not going to read all those numbers. So basically the point is that you sum over all these numbers so that they are 1, and then you apportion the probability proportional to the amount of distance from 0, more or less. Yeah, that's one of those things that I have like a really good intuition of, but I'm not good with the word doing. All right. You may recall that softmax was exactly what is used to create a probability distribution from a vector of real valued numbers, computed from summing weights times features in logistic regression in Chapter 5. This means we can think of a neural network classifier with one hidden layer as building a vector h, which is a hidden layer representation of the input, and then running standard logistic regression on the features that the network develops in h. So h is the hidden layer, and then we have a vector, and then we do logistic regression on that, more or less. Yes, Chance said this can be an exercise for us later. Yes, and we can read Chapter 5 at some point in the future, but I thought this was going to be the most directly relevant for a lot of folks. By contrast, in Chapter 5, the features were mainly designed by hand via feature templates. So that would be like, I'm trying to think of a good feature template. So if we're like trying to decide if a dog is healthy or not, we might be like, well, what's its pulse? You know, is its coat glossy? Yes or no? You might look at the gums and be like, are the gums nice and pink or whatever? So a neural network is like logistic regression, but A, with many layers, since a deep neural network is like layer after layer after layer of linear regression classifiers, and B, rather than forming the features by feature templates, the prior layers of the network induce the feature representations themselves. So the big benefit of using neural networks is that you don't have to design your features by hand. You can just provide the data, and then they will become features from, whatever space it is that you're working in. Here are the final equations for a feedforward network with a single hidden layer, which takes an input vector x, outputs a probability distribution y, and is parameterized by weight matrices w and u on a bias vector b. Why do we have two weight matrices? Oh, right. The final weight matrix is the for the output layer. So W is this first weight matrix here, going from the input layer to the hidden layer. U is the weight matrix going from the hidden layer to the output layer. So the hidden layer is the sigmoid activation function of the input layer weights times the inputs plus the bias, and then the output layer is the output layer weights times the hidden layer outputs. And then once we're done with that, we take the softmax over the final layer to create a probability distribution. We'll call this layer a two-layer network. We traditionally don't count the input layer when numbering layers, but we do count the output layer. So, by this terminology, logistic regression is a one-layer network. Let's see if there's... okay, we'll try to get to section 7.4. Let's now set up some notation to make it easier to talk about deeper networks of depth more than 2. We'll use superscripts and square brackets to mean layer numbers, starting at 0 for the input layer. So this is going to be like an index where we have a matrix, I guess, of different layers, or a vector of layers. So W1 would mean the weight matrix for the first hidden layer, and B1 will mean the bias vector for the first hidden layer. N sub j will mean the number of units at layer j. We'll use g dot to stand for the activation function, which will tend to be ReLU or tan for intermediate layers and softmax for output layers. We'll use AI to mean the output from layer I, and ZI to mean the combination of weights and biases, WI, AI-1 plus B1. And AI-1 means that we're going to take the input from the previous layer, multiply it by the weights of the current layer, and then add our bias. The 0th layer is for inputs, so the inputs X will refer to more generally as A0. Thus, we'll represent a 3-layer network as follows. So Z is the first layer, and it's so this is going to be the first hidden layer, and it's going to take the inputs times. It's going to take the weights, multiply the inputs at the bias for the first layer, and then we're going to use the activation function G, apply that to the outputs of that first layer. And then in the second layer, we're going to take the outputs of the first layer, this A1, multiply it by the weights for the second layer, and add the bias for the second layer. And then we're going to apply our second activation function, which does not have to be the same as the first activation function. And then we will y hat. So this could be softmax. So this would probably be ReLU, and this would probably be softmax. And then this would be the final output would be y hat. Note that with this notation, the equations for the computation done at each layer are the same. The algorithm for computing the forward step in an n-layer feed-forward network, given the input vector A, is thus simply for I in 1 through n, Zi equals Wi AI-1 plus Bi. So this is that the outputs of a layer are going to be the weights for that layer times the outputs for the previous layer plus the bias for that layer. And then we're going to apply our activation to those outputs, whatever that is. And then y hat is going to be the output of the final layer, the output layer. That's probably a little bit of a typo as well. Looks like a LaTeX error. The activation functions g dot are generally different at the final layer. Thus, g might be softmax for multinomial classification or sigmoid for binary classification, while ReLU or tan might be the activation function g at the internal layers. Okay. That was a lot. I think I'm gonna wrap it up here, and we will come back to 7.4 the next time I do this. I don't know. Maybe I'll do it. Oh, I won't do it next Wednesday. I'm going to be traveling. Yeah, but the next time we have a reading group, I think we will pick up with section 7.4, which is on training neural networks. But we have learned what neural networks are, how they work, why a simple linear activation function can't capture the XOR, the logical XOR that we talked about, scroll all the way up here, and why you need a nonlinear activation function and hidden layers. And then we did a lot of sort of notation and talking about the structure of a deep neural network. So this is deep because it has a hidden layer, at least one hidden layer. And then we finally rounded up with the notation that we're going to be using for the rest of the chapter when we talk about training. All right, and I think that's going to be pretty much it. And yeah, thanks for joining me. Hopefully this was helpful for people. And I will talk to you guys. I'm going to be doing live coding on Friday, so I will definitely do that. And we will do the reading group when it happens. I do want to get a steady pace at the reading group because this is very helpful for me and I enjoy it. I'll talk to you guys later. Bye.